So thanks everybody for coming. It's my great pleasure to introduce Susan Clark. Susan was a graduate student at Columbia, where she got her PhD in 2017. That's Erica. And from there, she was a Hubble Fellow over at the IS at Princeton. And then she quickly became a faculty member at Stanford starting in 2021, where she runs the Cosmic Magnetism and Interstellar Physics group, which sounds awesome. And I'm very excited to hear more. So take it away, Susan.
Thank you so much. It's such a pleasure to be here. I've been having great conversations with lots of you all day. And thanks for the lovely introduction. I work with this wonderful group of people in my very long titled nascent group at Stanford, and with many others, but I won't at all have time today to do justice to all of their work. Oh, okay. We'll advance slides by clicking. But just to flash some faces and let you know that there is now a wonderful group of people at Stanford working on ISM and magnetic fields science. I am part of the physics department at Stanford and also part of CIPAC, this Cobley Institute for Particle Astrophysics and Cosmology. And so the story I want to tell you about today is about two things: magnetism and morphology. And I have titled my talk thusly. So the first place to start is with a statement that's hopefully very familiar to you, that magnetism is just ubiquitous in the universe, right? We are probably very familiar with the concept of magnetic fields associated with planets and stars. A lot of what I will talk about today pertains to the weak magnetic fields that pervade the interstellar space in galaxies, which we know, especially from observations of galaxies that aren't our own Milky Way, can be very ordered and coherent on even kiloparsec scales in spiral galaxies. And these magnetic fields affect just a bewildering range of physics, touching many different aspects of science that you might personally be invested in. And that means that any of these problems that you approach, you probably don't want to do so completely neglecting the role of the magnetic field. So magnetic fields play some still poorly understood role in assembling molecular clouds and eventually in the formation of stars. The fact that the ISM is magnetized means that the turbulence in the interstellar environment is magnetohydrodynamic, or at least can't be fully treated in a purely hydrodynamic sense. And magnetic fields, of course, affect the propagation of cosmic rays and their confinement to the galaxy, as much of their energy, and so forth. And so some of the biggest questions that we care about lead us back to needing to understand the structure and eventually, hopefully, the origin of the galactic magnetic field in our galaxy. When I motivate my science, especially for popular audiences, I often like to talk about this cycle of gas that we know occurs in galaxies and that drives the overall evolution of galaxies. This ability of the gas to transition between diffuse and dense states is what precipitates the eventual formation of stars, which then interact with the interstellar medium and contribute to a sort of life cycle of gas. And at basically every arrow in this diagram, and at all of the many other arrows I could have drawn on this, the magnetic field is usually the component that is least well understood in the physics of what is going on. And in a slightly more technical way of motivating what the sort of problems I like to think about, the ISM is also a fascinating physical system because of the range of scales that you need to care about in order to treat any particular problem fully, right? If you care about the formation of stars, you don't just need to know what happens at the point of beginning fusion in a protostar. You really need to care about evolution of gas on very large length and time scales all the way down to the tiniest scales that we can observe in the ISM. And so the good news for those of us that want to study magnetic fields is that observationally, we do have various probes of magnetic fields in the interstellar environment. We can measure Faraday rotation, right? This is the rotation of the linear polarization angle of light as it passes through a magnetoionic medium. We can observe that in the ISM. We can observe synchrotron radiation from charged particles accelerated in the galactic magnetic field. And then importantly for today's talk, we have two observational probes of magnetic fields in the ISM that are available to us because of the presence of interstellar dust. So the ISM contains a good amount of dust, by which I mean sub-micron scale chunks of carbon and silicon, etc. These dust grains on average are not perfectly spherical, and they find a preferred orientation with respect to the ambient magnetic field that they sit in. And that has two consequences for the polarization of light we measure. One is that background starlight, which usually is initially unpolarized, as it passes through this magnetically aligned dust grains, the dust grains preferentially absorb one component of the linear polarization of the light. And so if we observe stars in linear polarization in the optical or the near infrared, we can measure the orientation of the magnetic field in the dust between us and those stars. And then these dust grains are also thermally re-radiating emission, which is also partially polarized because of this preferred orientation. So measuring that linear polarization also gives us an imprint of the interstellar magnetic field. And so at this point, you're probably saying, well, this must be one of the easiest problems in astrophysics. Look at all these many ways that we have to measure and digest information about magnetic fields. But of course, that obscures one of the real tricky parts of this business, which is that each of these individual probes gives us incomplete information. Each of these is probing either the line of sight component or the plane of sky component of the magnetic field. Often we're measuring orientation, but not direction. And each of these is in general sensitive to particular phases of the multi-phase interstellar medium. And so for any given problem that you might be trying to work out, putting together the piecemeal observational evidence is a substantially tricky thing to be tackling. And there is, we've made great advances recently, including with science that involves measuring this polarized thermal dust emission, which the Planck satellite very helpfully mapped over the full sky at 353 gigahertz, which is a frequency that is dominated by this thermal dust emission. And I have one final piece of motivation for doing this type of work, which is that if you are sitting in the audience now and you're thinking, well, this is all great, but I'm a cosmologist, I really don't care about magnetic fields or the ISM or any of this. When you look at this image, you might not be seeing a very helpful way to study magnetic fields in the ISM. You might be seeing something a little more horrifying, which is a polarized, very bright foreground to polarization measurements of the cosmic microwave background. And so the current observational state of searches for particular polarization signals in the CMB, we now understand very well that the path to some of the science we would like to do with CMB polarization, in particular, the detection of inflationary gravitational wave B-mode polarization in the CMB, the path to that science is going to have to involve a very clear understanding of the bright polarization from the interaction of matter and the magnetic field of our own Milky Way galaxy. So we know now that in order to detect these faint polarization signals in the CMB, we're going to need to have a great understanding of this polarized thermal dust emission and also of the synchrotron polarization from our galaxy. And so this is the old saying that one person's treasure is another person's foreground. From my perspective, this puts us in an excellent win-win optimistic situation, because this means that the better we can figure out the structure and the physics behind the magnetic fields in the ISM, the better we're going to be able to characterize these polarized foregrounds for cosmological work. And conversely, these cosmology experiments are producing incredible data that we can use to make progress on this galactic ISM science as well. So no matter where you're coming to this colloquium from scientifically, I hope there will be some piece of motivation that captures your interest. And my goal for today is to talk about a particular approach that I have taken lately, which is to say that in the ISM, we often have really fantastic spatially resolved data. We have image space data of different tracers in the ISM that encodes a lot of the physics of what it is that we might be trying to figure out about a particular problem. And so we should be using this physical information in the spatial distribution of our tracers. Just as one example of that, this is from a recent Further Stars and Planets review that we wrote about filamentary structure in the ISM, which shows up in many different contexts and dominated by different physics in different contexts. But the study of that morphology can tell us a lot about what it is that is going on in different phases of star formation and in different contexts in the ISM more generally. And so for today, I want to talk about some of the work that we have done to extract this physical information from morphology of interstellar emission, and in particular from observations of 21 centimeter hydrogen emission in the Milky Way. And so this is a movie of data from a survey with Arecibo, Galactic H1, where the bottom and top of your screen are the boundaries of the sky as visible from the Arecibo telescope in Puerto Rico, and you're panning across all right ascensions as the movie pans. In addition to panning, you're also moving back and forth in velocity space. So you're moving back and forth along the Doppler shifted frequency line of this atomic hydrogen emission. So you see structure come into and out of view as the movie pans. And the point is that there is a huge richness of information in these observations that we can make. If I just took these data and handed you a power spectrum out of them, you would be disappointed in how much information I had thrown away.
Can I ask you a quick question about the movie?
Yeah.
What's the sort of line width that's being integrated over when you're doing this zooming?
Oh, that's a good question. Yeah, so each of these channels is a few kilometers per second. Okay. And then you're panning back and forth, not quite over the whole line where we have information, but just over about 20 kilometers per second in order to keep it interesting. And actually, you can sort of see that this is 3 colors, and so the red, green, blue components of the image are coded to 3 different velocity channels, which we use a lot, and that lets you shift and see several velocity components at once. And so the idea here is that there's information on the magnetic field in the environment of this diffuse gas, and also on the phase distribution of this neutral hydrogen gas that's actually encoded in the morphology of this gas emission. And so our goal my goal, our goal, all of us together over the next however many minutes, we're going to develop quantitative descriptions of this morphology and then use that to ask new questions of our data, new questions about the physics that we need to construct a certain understanding of the data to even be able to ask or conceptualize. And so the first example of this sort of morphological information yielding new insights on the physics of the ISM that I have for you is seems to me quite old now, back in 2015. The realization that the linear structure in this atomic hydrogen emission, in that movie that I just showed you, if you quantitatively describe the orientation of linear structure in those images, that's what's visualized on the top panel here in the sort of brushstroke textures. That orientation of the emission structures is very well correlated with the plane of sky magnetic field orientation that you can measure directly from the polarized thermal dust emission. So the bottom panel here, the brushstrokes, are from these Planck 353 gigahertz measurements of the polarized thermal dust emission. And in both of these panels, you also see these little white line segments. Those are optical starlight polarization measurements, which are largely probing the same magnetic field orientation. In the case of the stars, you are probing the field between you and the star rather than between you and the rest of the line of sight.
About how far away is that hydrogen typically?
That is a great question. No closer typically than about 100 parsecs, and no farther away typically than about a few 400-ish parsecs, because the bottom part of your screen, this right here, is 30 degrees galactic latitude, and the north celestial pole is just off the screen over here. So you're looking at a slice of the high galactic latitude sky. And at those, looking up out of the plane, we see the dust, and therefore the H1, the hydrogen, is between those distances. The no closer than 100 parsec statement is because the sun actually lives in the center of this local bubble. And so there's very little of this gas or dust getting closer. Yeah.
So even though this is neutral hydrogen that you're measuring, is most of this gas predominantly ionized?
The ionization fraction here is 10 to the -4, but that's actually enough to still couple this neutral gas to the magnetic field. Yeah, which means that that the fact that there is some connection between its structure and the magnetic field isn't surprising from that angle. What was surprising is how well coupled these seem to be, and that is part of what we are still figuring out physically. Yeah, these are great questions. Please keep them coming. So you can make a pretty picture like this. You can, of course, also statistically demonstrate how well coupled these two things are. And I got curious then a few years ago about whether something more could be said using the information that we have in different velocity channels or at different Doppler shifted frequencies along the line of sight. And so I'm going to explain this next part of the picture via this little cartoon analogy to the way dust polarization works. So I am no great artist, but here are a representation of dusty regions along the line of sight, along some distance axis, okay? And here are two cases considered. If along the line of sight, your dusty regions are sitting in a magnetic field that is oriented very similarly in these different regions along the line of sight, that sight line will tend to have a higher fractional polarization in the vector sum that you measure in your broadband thermal dust emission measurements. If instead your dusty regions are sitting in a very disordered magnetic field along the line of sight, the signal that you measure will be more depolarized. And so I thought, well, maybe there's an analogy here where even though I can't take a particular velocity channel at these high galactic latitudes and make a one-to-one mapping with distance, I cannot do that. Maybe it's still the case that if I measure the H1 orientation, the orientation of these neutral hydrogen emission structures in velocity channels, and as a function of different velocity slices, I still see that the orientation is very coherent. Maybe that is also a sight line that ends up with a higher fractional polarization in the dust. And maybe if the H1 is very disordered along the line of sight, maybe that's actually probing some of this line of sight magnetic field tangling that contributes to more depolarized sight lines in the dust. And so you can just do this, come up with some machine vision algorithm that measures the orientation of your H1 structures. We've already done that. Do this as a function of velocity channel and construct some metric for that, which is what's on that H or y-axis here. I called it H1 coherence because I couldn't think of anything better, I guess. And it turns out that that is, in fact, correlated with the measured polarization fraction in the dust. And so the idea here is that you can use the combination of the spatial morphology and the velocity distribution of your neutral gas emission to trace something about the structure of the magnetic field in 3 dimensions. Yeah.
So can you go, what's the color scale on the previous plot?
Oh yeah, this is just a 2D histogram. Yeah. So this is just normalized, and what you should pay attention to is the fact that you see a correlated looking blob here rather than a less correlated blob. And so we can put these different pieces of empirical correlations together in a model that will let us ask new questions of our data. That's really the goal here. And so a few years ago, Brandon Hensley, who at the time was a postdoc at Princeton, and I put together this model that we call the magnetically coherent clouds model. And really what this model is just a mapping. We defined a mapping between the observational plane that we have, which is neutral hydrogen intensity as a function of 2 spatial dimensions and 1 velocity dimension. And we just mapped those data into what we call velocity orientation space. So this is showing up okay on the screen, maybe better on Zoom. But the radially here, I'm plotting the velocity, the Doppler shifted velocity of the H1. The red top half of this circle is just increasing positive velocity. Here is increasing negative velocity. That is just a visualization choice, so that the local standard of rest is always at the center of any circle like this that I show you. And then what is plotted azimuthally is the orientation that you measure of these structures in the neutral gas. And so the idea behind this mapping is that if in the real 3-dimensional space, what is going on is that you have 2 dusty clouds or regions along your line of sight distance space. Those 2 regions are sitting in differently oriented magnetic fields. Then generically speaking, these will typically map to 2 different velocities along the line of sight, and so they will separate in a radial space here. And if they're sitting in different magnetic field orientations, we expect them to separate in orientation space. And so the idea is if we make this mapping, we should see that more magnetically coherent regions are more concentrated in this velocity orientation space. And so clouds is actually really sort of a poor name here. We're really just doing this mapping of the data. And so this is what one sight line looks like for the distribution of linear structure in H1 as a function of velocity mapped to this space. And this, it turns out, describes some of the properties of the data that we're hoping to probe. And so as you hopefully expect from what I just explained, if you take a sightline in the dust polarization data that has a high fractional polarization, what we tend to see in this space is that the H1 emission is very collimated in orientation space, even when it's spread out in velocity space. And if you take a low fractional polarization sightline, you tend to see more disparate chunks in this velocity orientation space. And I promise you that I did not just cherry pick the 2 pixels where this is the case. This is actually a statistical trend that we see in the data.
I have a question.
Yeah.
So the right-hand one, like, you wouldn't call that collimated between the blue and the like closer in red section?
Not particular. I mean, they're at 2 different angles. I would call it less collimated than that one, and certainly also including this blob. But yeah, you could turn that into a more robust statistic of how similar they are. Yeah.
Excuse me, but the spatial resolution in the data, I mean, is there some depolarization coming just because of averaging over regions that are?
Yes, there definitely is. And so actually here, the H1 data that we're using have a spatial resolution of 4 arc minutes. But of course, to do this, we have to take some larger beam. What we're taking here is a beam that is comparable to, this is about 75 arc minutes around this. So comparable to the resolution that you need to smooth the Planck data to in order to have a high enough signal.
So you've matched things.
That's right. But that also means that in this map, which is a map of the dust polarization fraction, you certainly have depolarization that is both spatial within the beam and line of sight, right? And analogously, you sort of have that here where you could spread out an orientation space, and you can also have different distinct components along line of sight. In principle, this sort of mapping could give you a way to try to separate those effects. Although I haven't gone very far down that path, I think it'd be a cool thing to try and disentangle, maybe also in higher resolution data. Great, and then once you have defined this space that you're going to map your data into, you're really just a little geometric decomposition away from having the Stokes Q and U, the Stokes parameters for linear polarization, that are now defined solely from the morphology of the neutral hydrogen. And you can weight by the H1 intensity. You think that that is a good proxy for where the dust is. The dust and the gas are pretty well mixed in the ISM in general. And then you can make a map that, instead of being a 2D picture of what is here, a little slice of the sky, now you have this funny thing that is Stokes Q and U from H1 morphology alone as a function of H1 velocity. And so you have this 3-dimensional map of something that is geometrically very related to the magnetic field structure, where the 3 dimensions are position, velocity. But you can use this to probe interesting things about the 3D structure of the magnetic ISM. And you can also integrate over that velocity axis in analogy to what you are forced to measure in the dust polarization from the line of sight integration that you are stuck with. You just make a broadband measurement of the dust polarization. And that lets you compare directly to what we measure in the 353 gigahertz data. And so on the left, this is from top to bottom, Stokes Q and U, the magnetic field orientation, and the dust polarization. And on the right are the corresponding measurements that are actual measurements from the dust. So everything on the left is purely from H1 morphology, and everything on the right is an actual measurement of dust polarization. And the sort of shocking and fascinating thing is that this model is reproducing a lot of the basic, especially large scale properties of what we measure in the dust polarization. And the key thing that makes this an interesting exercise to go through is that we understand exactly what has gone into this, and it's purely geometry and the spatial distribution of the H1. What has not gone into this is any sort of modeling of a dust SED or any dust physics whatsoever. And so that means, for example, that you can look at this funny construction of the H1 coherence and compare it to the actual map of the dust polarization fraction. And if you had come into this question knowing nothing else and you had just looked at this map of the dust polarization fraction, maybe you would have said, oh, look, the dust grains are more efficiently aligned in some regions of the sky than in others. Maybe some of the variability that you're seeing in this map of the dust polarization fraction is variable grain alignment in the ISM. But to the extent that we reproduce the same patterns on large scales in these data purely from the H1 geometry, that immediately tells you that that's not the explanation, right? That you are dominated, at least at those scales, by this geometric effect of depolarization, either within your beam or along the site. And so the idea here now is that we have constructed these maps that we want to compare to data in clever ways to ask new questions about the magnetic ISM. And I'm going to tell you a few examples of the sorts of things that we can learn from this. But we've also made these maps publicly available if you have your own ideas or just want to play around.
It's like the maps reproduce the geometry, but undershoot the dynamic range. It's consistent with, is there a simple reason explanation for it?
Oh, okay. Are you referring to the actual values here?
Yeah.
Yeah, okay. Those can't be compared directly because they are in completely different units, right? Like in order to put the H1 based maps into some unit that is
Oh, sure.
right, we'd have to assume something about this, but you absolutely could do. And you could use this as the backbone for some dust model, paint an SOD onto it. Yeah, but we haven't done that here. So the H1 based ones are still in units of Kelvin kilometer per second, which is a very funny unit to see a Stokes map in, but that's okay.
Is
yes.
it fair to say that the agreement in the galactic plane is not as good as it is at high latitudes? It's not bad, actually.
It is shockingly not as horrible as I thought it would be, yes.
So the physics there seems very different because there's a lot more going on, obviously, in the plane, but also that it works well for very long sight.
That's right. Yeah, I think there are a few things going on here. I mean, one is that this definitely performs worse in the plane, and you should absolutely expect that there are sightlines where the dust polarization is dominated by dust that is not traced by H1, right? There are molecular clouds in these sightlines, where you should see an absolute loss of correlation. However, one reason this doesn't look as horrible as you would expect for a particular sightline like that is that we're doing this at relatively low resolution in order to have signal to noise over the whole sky. And so that mitigates some of the effect of having a molecular cloud, say, in your path. I was still really surprised that this works, that you don't lose the correlation at sort of intermediate galactic latitudes as fast as I thought you would. And I think there's actually a lot more to be done to interrogate, when these maps disagree strongly, what information is that telling us beyond just the obvious limitations of a model like this. Yeah, I think there's a lot more to learn there. And one of the other ways that we can learn about our dust data here is to compare the statistical properties of the actual dust polarization maps with what we measure in these H1 based polarization templates. And so, for example, the Planck data measured a correlation between the dust total intensity and the E-mode component of the dust polarization. And they also measured an excess of the E-mode polarization compared to the B-mode polarization of the dust. We see the same things in the H1 based maps, and that's for a really real physical reason. So first, just in case you've managed to avoid talk of E-modes and B-modes for a while, I congratulate you if so. Just very briefly, you can decompose your polarization field into these E-modes and B-modes that differ in their parity properties with respect to the Fourier wave vector. So the E-mode is parity even, and the B mode is the parity odd component. And so the reason that you see, for example, this positive correlation between the dust total intensity and the E mode component of the polarization is because in the interstellar medium, there is a tendency for filamentary elongated structures in isotropies in the density distribution to be aligned with the magnetic field orientation. And that situation, if here, again, I'm sorry for my artistry, but this gray thing is a filament in the ISM. And this arrow is representing the magnetic field orientation. That geometry translated into dust polarization will give you a polarization structure like this. And that will give you a positive E mode signal if your polarized intensity is coming from this filamentary structure. And so this alignment, this preferred alignment between density structures and the magnetic field is giving you this TE correlation and this predominance of E over B. And that's again something that then you would predict from our H1 based method here, where the orientation of the density structures is the thing that is giving you the polarization orientation. And so it makes sense that that falls out of our data as well. Planck also measured a non-zero TB correlation over large angular scales and over large regions of the sky, which is odd. Haha, that's a joke. But that is a parity odd quantity, right? So it's a quite literally an odd thing to measure. And if you wanted to construct something like that from the same sort of paradigm where these correlations are coming from the correlation between density structures and magnetic field orientation, what you need now is a little misalignment between your long axis of your ISM filament and your magnetic field orientation. And what you need to have that not average to zero over large areas of sky is the handedness of that misalignment to have a preferred orientation. And I am going to spare you the very gory details, but this approach gives you a way to probe this idea in the interstellar medium, because now we have a template that is constructed from assuming perfect alignment between elongated intensity structures and the magnetic field. So we can take the difference in angle between that thing and what we actually measure as magnetic field orientation and interrogate this picture. And the long story, which can be found here, short, I really think we see evidence that in the ISM, it is this small misalignments between the anisotropic density distribution, magnetic field orientation, that is giving us this parity odd signal, which will be really fascinating to interrogate further, because what we really haven't answered yet is whether that is telling us that there is some physical preference for one-handedness over the other, or that is just the random draw that we happen to have from our vantage point on the Milky Way.
Wait, can you go back before you?
Yes.
I guess should I be identifying structure in the bottom difference map? Like, should I be paying attention to the like white blobby regions that I can convince myself I can see?
So, okay, this is a representation of the difference map to make the point that the prediction here would be one sign of TB from one-handedness of this difference, and the other from the other. And so the signed angle difference is what's interesting. The structure that your eye mostly sees here, because our eyes are very sensitive to large angular scales, are like whiter blobs here, right? That is what you're really seeing there is that polarization fraction map from earlier. You're seeing better signal to noise in high polarized intensity regions.
But I guess to the extent that you are measuring a preferred handedness, I should see more blue than red or more red than blue.
Yes, but it is so marginal that I would be very impressed here.
No, I can't. I have no idea.
Yeah,
I'm just
yeah,
saying it
yeah,
doesn't
no,
look like
exactly.
either of those things is true.
Exactly. Yeah. No. And this signal is very weak, right? So it's not as if the whole sky is blue or something like that. I mean, the other reason that we would be alarmed about that is that a good way to get a uniform misalignment over the whole sky is just to imperfectly calibrate your
Systematic.
yeah, but I mean, this is really important, right? Because a lot of these experiments are designed to look at the polarization of the CMB. The parity odd signal in CMB polarization is something that we look for to find cosmic birefringence, new physics. And one thing that you might do is assume that that signal is 0 for this emission in order to correct your calibration. So it is important to understand what's going on here purely from that. So, and so now we have a path basically where we can take our data, construct some model, and then compare it to what we actually measure that has properties of the magnetic field within it. And what I'm excited about now is to iterate on this process and tweak our model in ways that can inform us about what is a better representation of the dust polarization and what is a worse representation and why. And so my grad student, George Halal, is leading some of this work to explore the morphological parameter space to see actually what is it that's most predictive of the magnetic field geometry and dust polarization distribution that we measure. And that means that we can now go from any image space thing to a polarization template. So here is the Stanford logo expressed as E-mode polarization, in case that's something you were hoping to see today. And this also gives us a template that you can cross-correlate with your dust polarization data or your nominally CMB polarization data in order to make better descriptions of what you're actually seeing in the dust. And so George also led a very nice work in collaboration with the Bicep Keck collaboration to do this and characterize dust in their particular field. We can also probe the 3D structure of the ISM with this sort of approach, because now we have some idea of what the line of sight geometry of the magnetic field might be doing. And so we used this to look for a particular effect that we should expect in the ISM when we have dust clouds with different SEDs sitting in differently oriented magnetic fields along the line of sight. When you have that situation, you should generically expect a frequency dependence in polarization angle that you measure. And we can look for that effect with these H1 based polarization maps. Because basically we can take our H1 based maps and split the sky into some control sample where we think the line of sight is dominated by a single component of the H1 and therefore of the dust probably. And sightlines where we would expect this sort of effect to be the most severe. Two regions along the line of sight that seem to be in very misaligned magnetic fields. And from this sort of thing, we made a detection of this effect, this line of sight frequency decorrelation effect in the dust data that's statistically robust and that we were able to make because we had this H1 based way of looking at the data. And I want to briefly answer a question that you may not have realized that you had, but has actually been a whole argument in this field for some time, which is what actually is it that we're measuring in these narrow channel maps of H1 emission? So I have been referring to them as density structures, and I've been making comparisons to the dust where unambiguously what we're tracing in the total intensity is correlated with the density field. But actually for a long time in the H1 and in other spectroscopic, other theory of what you should be measuring in the ISM, there was this idea that if you take a narrow channel map, so I'm showing you here another one of these red, green, blue images where each color is mapped to a narrow portion of this Doppler shifted frequency space, here order kilometer per second. There was an idea for a long time that if you look at a narrow enough channel map of this emission, the structure that you see is actually not correlated with the density structure at all. but is what people have called velocity caustics, is actually just an effect of the turbulent velocity field moving emission into or out of a particular channel. So this is a picture that dates back to Lazare and Prigozhin 2000 and other works around that time. And there's been various theoretical work and some observational work that reports to see signatures of this. So this is, for example, showing you as a function of the channel width that you've integrated your intensity over, that you've integrated your emission over, what happens to the power spectrum of the emission that you measure. And the idea was that this was support for this picture because you move to a narrower power spectral index as your velocity channel gets narrower. This, if you believe this picture, then it actually really changes the theoretical interpretation of what we're seeing, right? That would mean that we're actually measuring the correlation between the magnetic field and the velocity structure of the gas. And that also means that if you take your map and you measure its power spectrum, you believe that you're making a measurement of the velocity power spectrum of the gas, which is what has been claimed for a long time. But this is a very testable idea because we have this dust emission that certainly knows nothing about the turbulent velocity field. It's this broadband measurement along line of sight. And so you can do this experiment. You can say, all right, as a function of the channel width of my H1 data, how correlated are my data with the dust intensity that's going to be on the y-axis? And the picture in the theory has claimed that by a few kilometer per second line width, that correlation should be zero. That actually you're no longer correlated with the density field at all. And so what I would expect, which is not really showing up here, but I'll try to show you with my finger, is some sort of decreasing trend as a function of narrower and narrower channels. But what you in fact measure is actually no sign of a decorrelation from these sort of velocity caustics at all. You get a slight dip at the very narrowest line widths we can possibly measure, or well, channel map widths, I should say, subthermal even, which is consistent with pure radiometer noise, just a little noisier down there, so you lose this correlation with the dust a little bit. But actually, the data are consistent with no sign of this velocity caustic effect at all. And I think what's really happening and why people got confused by what they measure in the power spectrum is that the H1 is a thermally bistable medium. You cannot ignore the fact that these data are structured by both the warmer gas, the warm neutral medium, and emission from the cold neutral component of the H1. And I think what was happening in this particular paper is that in these narrower channel maps of emission, more of the structure is dominated by this colder, preferentially smaller scale emission from this cold gas structure. And there's actually lots of other observational evidence to support this picture and to rule out the idea that these data are actually velocity caustics. And so briefly, I am excited now about how we can use morphology actually to probe this phase distribution, to probe this distribution of this gas into the cold neutral medium and the warmer component. And this is work that's been led by my grad student, Milky Way, which is, I guess, technically in press at Apogee right now. The best way to tell the phase distribution of a particular line of sight in the H1 is to have absorption line measurements towards some background quasar in combination with some emission line measurements. That lets you actually directly constrain the spin temperature of the gas and the thermodynamic state. We got curious about whether there is information about that phase structure encoded in the morphology of the emission of the gas in a region, a little channel map around a sight line where you have a direct measurement of the absorption line data. And we approached this using something called a wavelet scattering transform, which is just schematically described here. So you start with some image space data, in our case, a channel map of the H1 emission around some quasar. And the scattering transform here is just a series of wavelet convolutions and then some norm that you take. And you can do this for a suite of different directional wavelets at different scales. And you do this iteratively. So your first order is just a convolution of your data with some set of wavelets, followed by an L1 norm into a set of coefficients. But then you can take those and perform this scattering operation again into a set of second order coefficients that are going to encode these correlations between scales and angles. If this architecture looks reminiscent of a neural net to you, that was actually one of the primary motivations of people that started looking into this, was to understand the mathematical underpinnings of CNNs, et cetera. But what I like about it is there's no training step that is happening here. You are just making a morphological description of your data as a set of numbers, right? Which you can then use to ask different questions. We focused here in particular on sets of these wavelet coefficients where the two wavelets of the two different scales parallel to each other or orthogonal to one another, averaging over the absolute orientation, which we don't think we should have any physical reason to care about. And so this is just to give you some sort of idea of what sorts of morphologies these coefficients might be sensitive to by taking some data and then making a synthesis of what would happen to your image if you increased the coefficient where these things are perpendicular to each other versus the one where they're parallel to each other, right? So these are synthesis images just made by gradient descent, forcing you to increase one of these coefficients or the other. And then our goal was, all right, let's compute these quantities on a bunch of little cutouts of our data where we have these background quasar absorption line measurements, and then compare at a coincident velocity to the observer what the emission morphology might be sensitive to. And the punchline is that we find that this emission morphology, quantified here by the scattering transform, is correlated with the mass fraction of the cold neutral medium that you can measure directly from these absorption line data. So this is a big correlation plot. Scale is on the x-axis. The y-axis is telling you the combination of orientation at two different scales in your scattering transform. What you should take away from this is that we find evidence that the more parallel scales, the things that might be associated, for example, with more filamentary looking structure in your image space, are more positively correlated with this cold neutral medium mass fraction. The more perpendicular scales, which might be associated with more blobby structure that's less anisotropic, are actually anti-correlated with the presence of this colder gas in your data. And so this is a direct link between the emission morphology and the phase of the gas that you're measuring. This is a different way to verify exactly that. Now, instead of directly using those absorption line measurements, looking at the ratio of the far infrared to the H1 column as a function of these coefficients. And I'm really excited to see where that goes next. That paper is on archive now, but we are already, we have great designs of what this means we can do, because clearly now the optimal way to decompose our data as a function of phase is to use the spatial information, to not be limited only to the spectral information, which is what people have traditionally done. So I hope I have convinced you that observations of the morphology in the ISM contain a whole lot of excellent physical information. We can just figure out how to get at it and what questions we should be asking. We've shown that H1 in particular can probe the three-dimensional magnetic field structure in the ISM, and also the phase structure of this gas. This is has consequences for our cosmological pursuits, as well as teaching us fantastic things about the structure of the ISM. And we have much more to come in this space, so please stay tuned for that. Thank you.
Great, so we'll take questions for Susan. Also, if you're online, you can either write your question in the chat or raise your hand and I will be monitoring that.
Thanks for the great talk. This might be a naive question since I'm not really aware of the energy scales involved in the neutral hydrogen associated with the ISM. So the 21 centimeter line is fundamentally a product of the interaction between the spins of the electron and the proton in a neutral hydrogen atom.
That's right.
And that's essentially a magnetic dipole interaction. And then you have an additional magnetic field that's present in the ISM. So that external magnetic field, is it strong enough to change this 21 centimeter interaction? Something like, can you get Zeeman splitting in the 21 centimeter line or any other such
Yes,
effects?
that is a great question. You can, and actually Zeeman splitting of the 21 centimeter line is our most direct way to measure the field strength in the ISM. That wasn't on my first slide just because that was sort of focused on large area probes of the magnetic field that we have. But we have in both emission and absorption measurements of that Zeeman splitting of the 21 centimeter line. Now, what that gets you in the ISM, where you can't resolve the full line splitting, is actually just the line of sight component of the magnetic field. But it's a direct probe of the local magnetic field strength, right? Because that splitting is directly proportional to the field strength. And one of the other things we're working on in my group actually is in principle, if we can combine those measurements with something that constrains the plane of sky field strength, at least statistically, or something morphological that tells us about the viewing angle of the local magnetic field, then we should be able to make a better measurement of the total magnetic field strength, which is usually the physical parameter we actually care about. And so I hope that will bear fruit. It would also be very helpful to have a lot more Zeeman measurements than we do. But most of what we know directly about the field strength in the ISM, which is sort of corroborated by other less direct ways to measure it, come from Zeeman splitting of the H1, the 21 centimeter line, and then in the denser gas, most of the measurements are OH and CN, which are other species that are really conducive to this measurements. Yeah, that's a great question.
So what are the, I guess, prospects for doing sort of post-processing forward modeling from MHD turbulent simulations? Because it seems like, compared to most of the time when we're worried about resolution, right? These kind of scales in the ISM should be well resolvable in a numerical MHD turbulence model.
Well, yes and no, right? The limitation with simulations right now is that you have a choice between having the resolution that you want and having the physics that you care about. What you would love to really compare to these data is to have really high resolution simulations of the ISM that also have this multi-phase structure and magnetism. And that we do not have. Your other option is to just look at a sort of turbulence in a box simulation where you can get to really high resolution, but a lot of what we see in the data really depends on the phase structure of the ISM. And so it's difficult to make a direct, you're not modeling exactly what you see in the data. And so you need to pick your questions carefully, which is usually the situation we're in.
Right, yeah, but it's not even, I guess in the limit of in the limit of having no chemistry, but just MHD, there's nothing useful you can learn, even from sort of the first part of your talk in terms of looking at, correlations of filamentary structures along the line of sight and gas polarization.
No, there's plenty useful you can learn. I think what I would say is that it should not surprise us in any MHD context where the field is strong enough, right? Where you are that you see structure elongated along the magnet.
Sure.
Right? But we are seeing something very particular here, which we unfortunately don't reproduce in the simulations yet, which are these cold gas structures that are very aligned. Eventually, that would be an awesome thing to be able to forward model directly from simulations. Yeah, but you can still ask plenty of interesting questions. Yeah, for sure.
Can I ask about EE and BB?
Yes.
So the natural explanation for EE you said is that you get these things that are aligned with the long filamentary structure.
Yeah.
Planck measured this ratio at like 2.
Yeah.
And the question is there something special about 2, or is it just that's why did it come out that particular way? Is it
It's a really good question. I think what it is telling us is a sort of typical geometry of the density structure on these scales that Planck is measuring. For example, on large scales in our data, when we are matching scales as well as we can, basically, we see basically the same fraction. This is expressed as B to E, but this pink line is the Planck measurement over the same region of sky, and these data points are H1 based prediction. Now, what we're building from this H1 based model has a built-in scale to it, which is what scale are you most sensitive to for however it is that you're measuring the orientation of these structures. And so we can, in principle, we could construct different geometries that are sensitive to different scales in those data, and then you can sort of like push your hump of B to E in multipole space based on how you construct that. Which means that in principle, we could try to use that to probe what we think is actually physically the scale that dominates the structures that we see in Planck or any other dust polarization measurements. That's I think is as good of an answer as we have from the data right now. And I wouldn't otherwise say that there's anything particularly special about this exact number. But I think also what we need, that number that everyone quotes is just an average over large regions of sky, and it should vary, and it does vary patch to patch in the ISM. So there must be more interesting physics to pull out of that than we have yet. Higher angular resolution data would also really help, I think, for that interesting ways. Last question, Zach.
Yeah, for those filamentary structure you saw that's aligned with the magnetic fields well, can I assume that that's showing that the filaments is embedded like a pretty uniform magnetic fields?
That is a great question. And Minji and I will have another paper out very soon proving exactly this because, right, I've told you two things. I've told you that these structures are very well correlated with the magnetic field orientation we measure in the dust, right? And then I've also told you that these structures are preferentially cold neutral medium structures, which do not dominate the column in any given line of sight. And what those two things mean is that if the magnetic field in the bulk of the column, which is associated with the warmer gas, was doing something completely different than what's happening in the cold neutral medium structure, we should lose this correlation very quickly, right? And then you might say, okay, that's fine. The warm gas is just very turbulent, and the magnetic field is just very incoherent. And so you're mostly sensitive to what you see in the cold neutral medium data. That's why you have this great correlation. But I would say to you, the bulk of the column can't just be incoherent, because then you're adding total intensity and not polarized intensity. And we actually have a very strong constraint on that from the maximum polarization fraction that we observe in the dust, which is it's high. It's like 22% in the Planck data. So the combination of those two things, what Minji and I have done now is build a model to constrain how coherent the magnetic field structure must be between the different phases of the ISM to reproduce these data. And I just a little bit premature to put that into this talk, but it should be ready for public consumption very soon. So you'll have to invite me back sometime and I'll tell you all about it. Thank you.
Great, thanks Susan again.